Okay, let's look at number 3. A projectile launcher consists of a spring with a plate. Spring is compressed, and there's a pin. There are 3 positions A, B, C, so they'll change compression distance. And spear is launched upon release of the pin. Okay, then you have student hypothesizes that spring constant of spring inside the launcher has same value for different compression distance. It's kind of obvious because spring constant K is physical property of the spring, so it's like what is it made above, or length of it actually changes K, but not a compression distance. Okay. What I mean by length is the original length of the spring actually depends on K2. But if you do compression, K is not going to change. A student planned to test hypothesis, so spring constant does not change using the launcher. State basic principle or law student could use in design the experiment to test hypothesis. So probably you'll have to do potential energy of the spring, change it to kinetic energy of the spear, and spring constant K does not change in this process. Okay, so we'll have to use conservation of energy, right? So you can do conservation of mechanical energy. I'll just write a short form, you can elaborate. Using the principle or law to determine expression for spring constant, so you have to figure out how you're gonna express spring constant in terms of quantity that can be obtained from measurements. So you have to think about how to measure the variables and find out calculating spring constant. So I guess you have to design first. I can think of like 3 different ways of designing this. So first one is simply you change the spring compression level, A or B or C, then you shoot it. So you can say energy stored in spring when it's released will be kinetic energy of the spear. So in this case you can do 1/2 K X of spring compressed, so I'll say XS squared equals 1/2 mv squared. In this scenario, how are you gonna measure this? You can measure, if you look at the measurements, let's give you a simple overview. If you measure length and small distance, you may want to use ruler. Like in this case, compression of the spring is a few centimeters probably, so you'll use ruler. If it's somewhere between like over 30 centimeter to maybe 1 or 2 meter, I'll use meter stick. If you have to measure something much longer than that or much bigger than that, you want to use measuring tape. And if you want to measure mass, probably you want to use the balance, but the term you can use is triple beam balance. Now this is a little different. I mean, if you use motion sensor, you can actually get the position and velocity. This is velocity graph over time period, and this is position graph over time period. So you can get this right away. Okay, so I'll just give you 2 different approaches for this. So in this case, I can measure X this by a ruler. I can measure mass by the triple beam balance. Then I can measure velocity using motion sensor, right? So motion sensor, you can use it, motion sensor. And then you have to express spring constant K. So cancel 1/2. So K will be mv squared. These are all measured over x spring squared, you can do it that approach. And you probably have to say quantity to be measured is mass of sphere, and I'll use mass of sphere. You can say triple beam balance. And in this case, you have to measure velocity, the velocity of sphere at the launcher, right? And I'll just use V. And equipment to measure is motion sensor. And you also have to measure the spring compression, right? So distance spring compressed, spring compression, and I'll use X of S. Equipment to measure, I'll use ruler. I mean, that's the easiest experiment you can design. Second way is, because a lot of times you don't think of this motion sensor, you can actually get the answer pretty quickly, is you can actually make it vertical. So make a vertical, and let's see, the pin level was A, was the deep one, right? So there's, you can have A, you can have B, you can have C. So you can put a sphere there, you can compress to C, or you can compress to B, or you can compress to A. So you can change this, and then you shoot it vertically. So in that case, energy stored in spring becomes eventually gravitational potential energy, because at the end you have only potential energy gravitational, which is mgh, and kinetic energy will be 0. Again, using conservation of energy, you can say energy stored in spring initially will become the potential energy gravity, right? But there's a couple of things you need to be careful, because when you actually measure, if you measure the maximum height and you want to use as mgh max, and probably you'll measure this, but initially there is actually different level of potential energy, because at A you have that much of initial potential, at B you have that much of initial potential, at C you have that much of different potential. So probably for each different case, you want to choose reference level as where the sphere was started, okay? Or you can say 1/2 k x squared equals mg. Instead of writing h, you can say h max minus h initial, okay? H initial means you have to actually measure from the ground what was the initial level when the sphere is, okay? Because this is basically displacement. So if you do that approach, you can find out k by 2mg h max, or h final, I'll just call h final, minus h initial over x squared. And you have to measure mass. We know g 9.81 or 10. You have to measure final height. You have to measure initial height. But how are you gonna measure this? I'm not 100% sure. You can measure by, you can say you could measure this somehow. And x is the ruler, right? Using ruler, okay? So you can do that approach. In this case, probably you have to measure height final, height initial. Actually, I have to write height final, height initial, and you have to come up with like a measuring tape or ruler, something like that. Actually, third approach, I'll just show you third approach too. Third approach, let's go quickly. You can use a table. Let's say this is a table. You can definitely measure the height of the table, and you'll launch this horizontally, okay? Because all you have is x direction of velocity. The time to fall is actually the same. Okay, so I know this time. I don't think you need to really measure this because you can say displacement y is 1/2 gt squared. This came from displacement is v on t plus 1/2 at squared. But for initial y direction velocity will be 0. So basically in the y direction, you only have gravitational acceleration. So this is like a short form. And this is basically height of the table. Right? So you know this time. You can measure it if you want, but you know this time by just looking at it. I know time to fall will be 2, this is height of table, 2 height of table over g square root, right? And definitely you can measure this distance. If you can measure this distance because I know Vx will never change while falling. So you can figure Vx is x, this is x, I'm gonna call this x displacement, y, x displacement over time it takes. But time it takes you can actually measure from here. So you can say x displacement over radical to h. Remember this was height of table over g. So you can calculate like this way. Then you can again come up with 1/2 kx squared, which is energy stored in spring. Again, this is the compression distance you can measure, equals 1/2 mv squared. But instead of using motion sensor to get this velocity right away, you can actually calculate like this. You can put it, but if you use the third method, your calculation gets a lot more complicated, okay? And I think that's basically everything for this question. Let's look at describe overall procedure to be used to test hypothesis. So you'll have to say like you compress on different distance, and you runch it, and you measure either velocity by motion sensor or maximum height. In this case, you have to measure initial height too, or x displacement if you use the third method, okay? And probably you want to say you repeat this, several times and use the average of that to reduce the error, okay? And I think I'll let it answer this, right? Because you have to realize once you calculate this, I think we calculated expression for k for the second part when you shoot it vertically. I also went over k for the first part when you can measure the velocity. And for each different cases, for each different x, when you measure x and when you measure b, you have to realize your should come out where k is constant for each case. Okay, so if you measure this, measure this, measure this, measure that, if you put it in, your k is always same no matter how you change x. All right, so I'm gonna concur with that. And let's check the last part. Another student uses a launcher to consecutively launch several spheres that have same diameter but different mass, so you have same size. Each sphere is launched from position A. Consider each sphere launch speed, which is the speed of the sphere, is contact. Okay, so basically all the energy is stored in spring constant. So I don't really care what mass you have here. Initial energy is actually stored in spring, so they're all same. So it's basically 1/2 k x squared, and this is now fixed because right now you're using position A. Now eventually this becomes kinetic energy of this sphere, which is 1/2 mv squared, but this value is same, but if mass increase, obviously velocity has to decrease, okay? Because these quantity has to be always equal. And let's see how you can graph this, because you have launch speed on the y-axis, so this is y-axis speed. In x-axis you have mass, so you have to isolate velocity and you have to isolate mass, right? So you have to solve for velocity, I guess. So you can cancel 1/2, then you divide by mass and you take square root. So basically v squared equals kxa squared over m. But in here, k is constant, xa is constant too, because that's the distance of the compression at pin level A. The only thing changes actually m. Okay, so you have v equals square root of, I'll just write in front, square root of kxa squared, but remember this is constant, times 1 over radical m. Okay, so it's like y is proportional to something like 1 over radical x. And this is inverse proportion graph, right? And this graph, if you think about it, if x is 1, for example, if x is 1, y is 1. If x is 4, y is 1/2. If x is 1/4, this come out as 1/2, and that will becomes, if x is 1/4, this will come out as 1/2. So 1 over 1/2 will be 2. So when it's 1/4, it's gonna go up to 2. So basically your graph looks something like that, okay? And whatever I have here is multiplier, okay? This is like a constant, like a slope. So what it does is, if this value was say 2, for example, and everything doubles up, so this doubles up to here, this doubles up to here, this doubles up to here. So what happens is the graph will actually move outward, okay? So it's gonna something like this. So I think that's good enough, right? So you can sketch like that, okay? So that's 1 over radical x inverse graph, okay? All right, that was it for this test.